Now, it would be pretty boring if we just limited ourselves to graphing regular old sine of x and regular cosine of x. So instead, what we're going to do is we're going to introduce a series of constants that perform transformations of those graphs, very similar to what we did with other types of functions earlier in the year. So we did this to parabolas, where we moved them around. We translated the graphs left and right. We applied dilations that stretched them in the horizontal and vertical directions. We did this with square root functions as well. We did this with absolute value functions. Those were the first ones that we gave this treatment to. And so now we're going to do the same thing with sine and cosine graphs. The catch is the terminology when we apply these same types of transformations to sine and cosine is different. We don't use translation for the horizontal direction. We do for the vertical, but not for the horizontal. We don't use dilations at all as the term of choice for that type of transformation when it comes to sine and cosine. But the effect, even though the terminology is different, is the same as what we had done before. So first off, we have the amplitude. Really, this is just a vertical dilation. So what the amplitude is going to do is it's going to stretch the graph or shrink it in the vertical direction. And so you can see that's represented by the constant A in our equations up above. So here we see two sine waves. The first is the red one, y equals sine of x. That's just our original graph that we generated using the table earlier. It starts at 0, it ends the cycle at 2 pi at 0, it's at 0 halfway in between, with a maximum at pi over 2 and a minimum at 3 pi over 2. Those high and low points are at 1 and -1. But in the blue graph, once we introduce that 2 out in front as the amplitude, now we can see that the period is the same. We're still starting and ending the cycle at 0 and 2 pi, but the wave is 2 bouncing off of 2 and -2 as our high and low points of the graph, as our maximum and minimum points, instead of 1 and -1. The second transformation is our horizontal dilation from before, but now it's called the period change. So now, instead of taking a distance of 0 to 2 pi to complete a full cycle, we're going to either extend that or squeeze it into a shorter period of time along the x-axis. And so what we're going to do is we're going to calculate what is the period of the graph. How long along the x-axis does it take for the graph to cover an entire cycle? And so the coefficient that has an impact on that is b. And so that's the number that is multiplying the x or the input part of our function. And so you can see that we use b to calculate the new period by taking 360 degrees, if we're graphing in degrees, or for the most part we'll be graphing in radians. So we divide 2 pi by whatever that number is to figure out what the new period is. And so as it'll turn out, if b is less than 1, if that number is a fraction like 1/2 or 1/4, it's going to end up increasing the period, because when we divide 2 pi by that number, we're going to multiply by the reciprocal, so it's going to make the period larger. And then if that number is bigger than 1, then it's going to decrease the period. It's going to squeeze the graph, so it's going to pass through its full set of values faster. So for example, if we take a look at the two graphs that are here. So again, the red one is our original. We can see that it starts at 0, it ends its cycle at 2 pi, it passes through this full set of values over that length. If you look at the blue graph that now has a 2 in front of the x, if we divide 2 pi by 2, we get pi. And so that's now the new period of this graph. And so as a result, you can see that the blue graph is moving through its set of values faster. Instead of starting its cycle at 0 and finishing it at 2 pi like the red graph does, the one that's highlighted, now it's getting through that full set of values in just a distance of pi along the x-axis. The remaining two transformations are our translations. So these are the constants that will move our graph from left to right or up and down. And so those show up as h and k in our equation. So k, if it's a number that's added somewhere after the equation, outside of the sine or cosine, then that number is going to move the graph up or down. So we call the sinusoidal axis. So like the line that the graph bounces up and down, above and below on our parent graph is the x-axis. So that's the sinusoidal axis. Well, that zero line, that central line, can be moved up or down by adding a number or subtracting a number k to the equation. And then the last transformation that we'll explore a little bit later is the phase shift. So this is the horizontal translation. So that instead of starting the cycle at the y-axis, in the case of sine, it would start from 0 and go up. In the case of cosine, it would start at the maximum at 1 and go down. Now we can move where that starting point is to the left or to the right.